Okay, so last time we had some issues with inputting some things on Wiley, and I spent last night chatting with Wiley over the internet to figure out what was going on. And of course they're not straightforward about anything. And I'm like, well, this is just something that's come up. And they're like, oh, it's the student's computer. Oh, it's this, it's this. I'm like, well, I've had multiple students have this. It happened on my computer type thing. And then I was like, did you guys do an update? And he's like, well, we did do an update over the weekend. I'm like, well, why couldn't you just start with that? Like, so he said that in, I think it was 3.6, we were having issues, right? That e to the 10 minus pi.
That's not an issue.
Oh, okay, so e to the 10 minus pi was the correct answer there. And we didn't have that submit button. Or some students are complaining that there is no submit button, or when they submit, nothing happens. You guys have that issue?
Yes.
Okay, so the developers at Wiley had said that you need to clear your cookies. So if you go in there and clear your cookies, then it should fix the problem.
Did it fix your problem?
It did. So that's something. Right, remember last time we couldn't, and I tried this in the other class, I couldn't input anything here. If I did, nothing happened. I hit submit 5 times, nothing happened. I saved it, went back, and it was gone. It was probably from that software update they did over the weekend. So I don't know too many details of it. Another thing students are complaining about is Wiley's putting an A in your problem. Do you guys have that? Has it been on problems with e to the power or on other types of problems as well? E to the power. Yeah, so I noticed on 3.1 number 21, specifically this one was, or maybe it wasn't 3.1, 3.2? I remember it was 21. Okay, so it was this problem. A lot of you, I could go in your grade book and see every attempt, and a lot of you had A's in there. So I was talking to the Wiley people, I was like, well, what's going on? And he's like, well, maybe it's keyboard error. I'm like, I'm pretty sure not 20 of my students are accidentally hitting A when they should be hitting 9, right? And so finally they're saying that it could be the type of keyboard you're using, which doesn't make sense to me at all. They're looking at it, they sent it on to their tier 2, I don't know, programmers or whatever they call them, and they're trying to fix that. So if you had submitted this, some of you, I saw like you had some A's and then you went on your 3rd or 4th attempt, you got it to work. So I don't know what you did, if you cleared your cookies or, I don't know, changed browsers. One student had said they went from Explorer to Google Chrome and it worked. So if you get it to work, that's fine. You have your point there. So Wiley is meant to be beneficial to you guys. If you turn in written homework, I might grade 1 or 2 problems. If you have no clue on those problems, you get, 5 points off or 10 points off a 20-point assignment. You get 50 points. You get 50% of your grade for that assignment when you did most of the assignment. So Wiley was put into place so you get instant feedback. Yes, you're doing this right. You understand what you're doing. And you also get points for every problem that you do. So you get some credibility to doing the assignments. Versus before we do written homework, a lot of students wouldn't do it because I would only grade 1 or 2 problems or even 3 or 4 problems, and you do 20 problems, you just don't see the benefit in that. So Wiley is meant to benefit you guys. Some of you are using it correctly, some of you are using it incorrectly. I can't combat that if you wait until your 3rd attempt to see the answer and then plug in your points. If you plug in something wrong, I'm not giving you points back. If you just make a negative error and on your 5th attempt and you want your points back, you're not going to get it. Unless you've attempted the 1st, 2nd, and 3rd all the way through, and if you do something small, I've given points back no problem. Or if you didn't simplify. But if you go hit 3 submits to look at the answer key and want points back, it's not going to happen. So don't abuse the system. This has been something we've had to deal with from the beginning of solution manuals, right? Everyone has a solution manual, they copy it down, they think they understand calculus, come to the exam and they're failing. They're like, oh, I get A's on my homework, why do I fail? You know why you get A's on your homework. So that being said, Wiley's worth 15% of your grade. Majority of the time, last semester, out of my 40 students, I think 32 of them had 100% on Wiley. So if you keep with it and go through it, you're going to get your points for doing it. So it's not meant to trip you up. It's not meant for you to spend 30 minutes on trying to figure out why there's an A in the problem. Keep me in the loop, keep me aware of what's going on. I can keep Wiley aware, and the system will be a little smoother. So don't get frustrated with the system. It's not meant to frustrate you guys. It's meant to give you the feedback, yes, you're understanding this correctly, you know what you're doing, type thing. Okay, so that was my spiel on Wiley. I emailed out the study guide for exam 2. Did you guys get this? I've also posted it in Blackboard, so you have a couple electronic copies of this. And I kind of want to go over section by section. Some of the sections I grouped together because it's concepts. 2.2, the derivative function. You will be given a derivative function problem by the definition. So this is the important part, the definition. I try to write my exams to prepare you for final exams. So if you go to final exams, that was actually last semester's exam. If I look at the 2012, this is an example of how I could ask you to find the definition of the derivative. So use the definition of the derivative for the properties of limits to find the derivative of this function. What is the derivative of this function? Yeah, right? Negative x to the x, or negative x to the negative 2, or you could write that as minus 1 over x squared. So you know the derivative, but you have to show that work using the definition of the derivative. So if I want to write this out, if I'm given the function f of x equals 3 plus x to the minus 1, and I'm asked to find the definition, or use the definition, that's the important part, to find the derivative. The definition of the derivative, f prime of x, is defined as the limit as h goes to 0 of f of x plus h minus f of x over h. That is the definition of the derivative. So applying it to this function, we get the limit as h goes to 0 of 3 plus 1 over x plus h minus 3 plus 1 over x, right? Quantity of that over h. Does anyone have any questions where that came from? So now I need to find a common denominator, simplify, take the limit as h goes to infinity, or sorry, h goes to 0, and then get my answer. And my answer should be, my answer will be minus x to the minus 2, or we can write that as minus 1 over x squared. So you know what your answer needs to be, you just need to get there.
So, are you okay with us just writing that out and just
No, you need to simplify it and you need to show it. So the next step here, I'd have the limit as h goes to 0. The 3's would cancel, right? And I'd have 1 over x plus h minus 1 over x over h. Get the limit as h goes to 0. Find a common denominator. And simplify, right? So this is really, I flip this and multiply. So once I find the common denominator, I have x times x plus h, but then when I flip and multiply the h in the denominator, I get the h still in the denominator. So the limit as h goes to 0 of minus h over x plus h times h, and that cancels the h in the denominator with the h in the numerator. So I get the limit as h goes to 0 of minus 1 over x plus h, which gives me minus 1 over x squared, which is what I want. So I need to see all this. It needs to flow. You know what the answer is going to be. You need to show that by using algebra and the definition of the derivative.
So there'll be something like that on the test.
Yes. In the last 2 semesters, no, the last 4 semesters, last 2 years, there's been a definition of the derivative on there. So in the past, I've graded this one on the final exam. The last couple of semesters, I've graded this one. And some students will try to explain what they're doing, like, oh, I'm taking the power of x down, multiplying x by the power minus 1. They think that's the definition, and that is concerning. This is the definition. So showing this work, writing this will give you some points to start with. Saying they understand this is the definition, you get some points. Then plugging in the function correctly, you get some points. Simplifying, you get some points, and then actually getting your answer. If you just write your answer, you don't have any points. So there's partial credit there.
I mean, did you give those students?
No. But then it turned out it was really kind of unfortunate because their instructor had never gone over the definition with them, and so they were just going. So we ended up curving it for them. But yeah, because 10 points, and probably 99% of that section got minus 10 because they didn't know the definition of the derivative. So with some coordination, we want to give you guys the best. I want to give you guys the best chance of getting the highest percentage on the final exam. So try to tailor my course to how the questions are going to be asked on the final exam. So, warning, no other formula for the derivative may be used in the problem. That doesn't mean that you can't check your answer with knowing what the derivative is, right? But if you just say this is the derivative and you don't show any work, you won't get any points. Any questions on definition of the derivative? Just do some examples and actually write through the steps. Like square root of x, what's the derivative of square root of x? You know the derivative of square root of x, but showing it algebraically might take some practice. So if you look in this section this is 2.2. This is over 2.2. So if you look at problems in 2.2, basic polynomials, like if I say x squared plus 2x, you know what the derivative is going to be. But expanding all that out, getting it to cancel correctly, just give your, do maybe 1 or 2 problems before the final exam with the definition of the derivative. Question?
On Wiley, it was delta x over delta.
Yeah. Wiley gives you just 2 different versions of the definition of the derivative, and that would come up when we were talking that local linear approximation with delta y over delta x with the definition of the derivative, but you're not going to have to do anything like that. This is the definition of the derivative we use. There's multiple versions, and if you want to use a different version and it's correct, that's fine, but I won't force you to. This one is by far the superior one, so you don't have to factor out a quantity x minus 5 if x is going to 5 type thing on top and bottom. Here you just factor out an h, which is a lot easier to deal with. Okay, that's 2.2. 2.3, 2.4, 2.5, and 3.2 are all basic differentiation. Can you use the product rule, the quotient rule, the chain rule? Can you take the derivative of the sinusoidal functions, sine, cosine, tangent, secant, cosecant, cotangent? Can you differentiate e to the x, and can you differentiate ln of x, right? So if we pull up old final exams, this gives you good indication of what you're going to be asked. So a lot of times, they just give you a function, and they even tell you, do not simplify your answer. So take the derivative of the first term, term by term basis. So know how to differentiate anything in here, right? So this is all chain rule. Chain rule, the chain rule. Derivative of a square root function, the derivative of ln of a function, and sine squared, which is a chain rule. If I pull up here, it's along the same lines, you're finding the second derivative. So know how to find the derivative when you have, fractions, x to a fraction. Derivative ln of x to the fourth. Right, and then once you get that first derivative, you can find the second derivative by differentiating that function. But usually there's a whole page of them on the final exam. So be able to differentiate any of these functions, right? And the forms are all the same, the functions just change, right? If I'm multiplying two functions together, I take the derivative of the first function, hold the second one, plus the derivative of the second one, hold the first. Now, if the function sine or e to the x or ln of x, I deal with that when I differentiate it, right? This is an example of a quotient rule. Derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top. And this is an example of a chain rule, mixed in multiple ways, right? So the derivative of the outside function would be minus 1 this to the minus 2, times the derivative of the inside, which would be cosine of this, times the derivative of this inside, which would be 8x, right? Do you guys see the layers there?
What do we do with that 3?
Well, the 3 here, when I take the derivative, yeah, it would be 0, but it would still be there. Yeah, so if I want to find the derivative of y with respect to x, and y is 3 plus sine of 4x squared plus 5 to the minus 1. So if I want to differentiate, then y prime is going to be minus 3 plus sine of 4x squared plus 5 to the minus 2 times the derivative of the inside. And the derivative of the inside, this whole function would be 0 plus cosine of 4x squared plus 5 times the derivative of its inside, which would be 8x.
Just real quick,
Mhm.
you went through the product rule and the
Mhm.
quotient rule,
Mhm.
but I think
So-
quotient rule, you said this, that it's the derivative of the top
Mhm.
minus the derivative of the bottom.
Derivative of the top, hold the bottom,
Right,
minus
right,
the derivative
minus.
of the bottom, hold the top, over the
Isn't it
bottom
all
squared.
over the bottom square?
Yes.
Okay.
So if I just kind of write out the forms, if I have f times g and I want to differentiate, that's the derivative of the first function, hold the second one, plus the derivative of the second one, hold the first. If I have f over g and I want to differentiate, it's derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top, over the bottom squared.
Right. Okay.
Right? And then the chain rule, if I have f of g of x, which this is a little bit different to see, it's the derivative of the outside evaluated at the inside times the derivative of the inside.
In as many
Layers as there is.
Russian nested things.
Yes.
Okay.
The derivative with respect to x of e to the u would be e to the u times du over dx. The derivative with respect to x of ln of u would be 1 over u times du dx, where u is a placeholder for a function of x, right? So then I could have any combination of this. I could have e to the x times sine of x. And then I would do the product rule, derivative of e to the x, hold sine of x, plus the derivative of sine of x, hold e to the x, and I would have my answer there. Question?
You had one that was ln x to the fourth.
Yes?
So is that just like, would that end up being 4x to the third over x to the fourth?
Yes. So this would be 1 over x to the fourth times 4x cubed. So I'd write that as 4x cubed over x to the fourth. So I could write that as 4 over x. Yes. So a lot of times the simplification comes in handy when it asks you to then find the second derivative. Because finding the derivative of this function, I'm not even trying to use the quotient rule, it's going to be time consuming, but really this is just the function. What's the derivative of this function? Minus 4x to minus 2, right? And it's not as clear here. So simplification is really beneficial when you go to take the second derivative. Question?
Can you get a derivative of a number to the x power?
A number to the x power. So that's this example, right? E is a number. So if I take the derivative with respect to x, let's do 2 to the x power. This is 1 over ln of 2 times x, right? Do you guys remember that? That's the form, right? And then we said it's really nice when our base is e. Because e is just a number. Because ln of e is 1. So this is the exact same form here. So if I had the derivative of x squared of, let's say, 2 to the sine of x. Oh, not 2, not e. 2 to the sine of x. You would treat this just like e to the sine of x, except you would have 1 over ln of 2 out front. Right? So I'd have 1 over ln of 2 times sine of x times cosine of x. So this would be 1 over ln of 2 cotangent of x. Question?
That one where you took the derivative on the very top,
Yeah?
how would you do the second derivative
Here?
at the very, very top one? The 3 plus.
This one?
Yeah.
Well, the second derivative of this one would be quite a bit more messy, right? Because I have a function times a function within a chain rule, right? So I would say, okay, I actually have 3 functions multiplied by each other because I have x times cosine of a function times this whole function. So I wouldn't ask you for a second derivative here.
But if you were to do like the negative 2, you just hold everything else,
Yes.
and then you just go through.
Yeah, so you take the derivative of this function, which would be 2, this times minus 3, hold this function, plus the derivative of this function, snowball. So it would be relatively painful to do.
It's going strong to the E to the U.
What?
Yeah, this one, I don't really understand how these related.
This?
Yeah.
How are these related? These are related because it's both of a number to a power versus a variable to a power, right? X squared is a variable to a power. Here we have a number to a variable. E is a number. But the nice thing about e is ln of e is 1, so we don't have any coefficients to worry about. Here, I have to keep in mind, I'm going to do a change of base here, and then when I do that, I get 1 over ln of 2. So I say, here? Yes.
So we have to first take ln of 2x.
No, this is ln of 2 times x.
I think he's saying how to get a 1 over.
That's the form. 1 over ln of 2 times 1 over x. That's the form. For ln of, oh, yeah, I don't know. What am I doing here? Should be, yeah, no, there's no 1 over here. This is ln of 2 times x. Sorry about that, guys. There's no 1 there. I'm doing this problem. Yes. Yes. Sorry about that.
Wouldn't it be 2 to the x or 1 according to the denominator? It is ln times b to the x, so times 2 to the x.
You said ln?
Yes, of that thing, which is 2x, ln of 2
ln of 2.
times 2 to the x.
No.
No?
This is ln of, this is the x times ln of 2. Ln of 2 is just a number. Same as like 5x. Amanda?
So is the next one on then 2, the 20?
Yeah, that would just all be times. Sorry. I'm pulling 2 different things there, yeah. So yeah, this would just be 2, this would be ln of 2 sine of x times cosine of x, right?
Okay, I was wondering why you didn't ring the bell.
And this would be 2 to the x. Oh, my goodness. Okay, let's start again. So 2 to the x is 2 to the x times ln of 2. So the derivative with respect to x of 2 to the sine of x would be 2 to the sine of x ln of 2. 2 to the sine of x times cosine of x times ln of 2. right?
Yeah, this is the form that I know.
That's, yeah, so sorry about this. I was,
So the ln of the function multiplied by derivative.
yes. So that
you
is,
hold the second one, or you make it as it is.
yeah, you leave it, like, just like e to the x, right? The derivative of e to the x is e to the x. But the only thing different here is you're going to have this ln of 2 on both times. Because really we'd have ln of e, but ln of e is 1. Does that make sense? Sorry about that, guys.
Where's the ln?
The ln of 2 is because I'm doing a change of base here. To get this in the form of e to the x.
Where's the x go?
Where does the x go?
It's 1.
Oh, it's the derivative of x is 1.
Yeah.
Gotcha.
Does that make sense?
Can we do another one? Because there's still.
Okay, so honestly, there's not a lot that comes off from base 2. Everything's base e. Right? So we did an example, you know, if I have e to the secant of x. What is the derivative of e to the secant of x?
E to the secant of x.
X, negative secant,
That would just be
tangent, right?
tangent.
It would be secant tangent, right?
Oh, no.
There's no negative. Does that make sense? If this was, instead of e, if it was 2, then you would have an ln of 2 tacked on here. Or if it was 5 to the secant of x, you would have an ln of 5 tacked on here. But it acts the exact same as e to the x, except you have that ln of b.
And then you're taking the derivative of the x.
Yes. And that's what it's saying here. If I take the derivative of e to the u is e to the u times ln, or times du over dx. Question?
What would be the derivative besides sine, cosine, and tangent?
Yeah. So the nice thing about it is you can always derive it within about 30 seconds if you really needed to. So let's say, what is the derivative of cosecant?
Negative cosecant squared. Cotangent.
So even then it's like, ooh, did I remember it correctly? This is the correct answer here, but if I wasn't for sure, I could just say, okay, I'm going to write this as 1 over sine and use the product rule, or the quotient rule. The quotient rule is the derivative of the top, which is 0, minus the derivative of the bottom, so I get minus cosine of x, over sine squared x, right? So to verify this is the same, if I have cosine of x over sine of x times 1 over sine of x, it's the same thing, right?
Yep.
Sine over cosine is cotangent, and 1 over sine is cosecant. So it is the same thing there. So if you left the answer in this form, you would still get full credit. That's fine. If I just asked for the derivative of cosecant. But I might say, what is the derivative with respect to x of x squared cosecant of x? Then you have to use the product rule. The derivative of the first, hold the second, plus the derivative of the second, hold the first. So if you don't remember the derivative of cosecant, take 2 seconds and find it. It doesn't have to be in this form. But it's nice to remember in this form, then you don't have to derive it type thing. But if you're not convinced you know it exactly for sure, take 2 seconds and show it.
So we don't need to learn anything about the tangents, like the line.
So everyone, yeah, so that was a popular question in the last class as well. Will I ever ask you for an equation to the tangent line? Possibly. The equation to the tangent line is a very staple part of Calc 1. And as long as I give you a point and give you enough information to find the slope, which is the definition, the derivative at the point, you should be able to find the equation of the tangent line, right? The equation of the tangent line, you need a point, so x comma y, and a slope. So your slope is going to be the derivative at, let's call it x1 comma y1, at x1. So the equation of the tangent line is y minus y1 equals f prime at x1, x minus x1, right? There's nothing new there. You guys have been doing that since middle school, probably, right? Equation of tangent, point slope form for the equation of the line. So the only new thing here is how to find the slope, right? So I've seen this come up in final exams before with logarithmic differentiation. So I don't remember, I think it was maybe 2009. Here we go, this is a good one. Write the equation of the tangent line to the curve at the point. To be able to find the slope, you have to do implicit differentiation, right? Implicit differentiation, section 3.1, right? So if we come back to our sheet here, we've talked about the techniques of differentiation, the product and quotient rule, basic derivatives of the 6 trigonometric functions, and derivatives of e to the x and ln of x. Those are all just forms. 3.1 is implicit differentiation. So if I want to look at an example of implicit differentiation, this problem, I have to use implicit differentiation. One step further from that, after I got my implicit differentiation, I plug in x equals 1, y equals 2 to find the slope. Then you have a point and a slope, finding the equation of the tangent line, plug it in point slope form. So if I have 5xy cubed minus 8y squared equals 8, and I want to find dy dx, the only way to approach this problem is implicit differentiation. So I have 5y cubed plus 5x times 3y squared times dy over dx minus 16y times dy over dx equals 0. That's the calculus, right? Derivative of the first function, hold the second function, plus the derivative of the second function, hold the first function, but when I anytime I'm differentiating y, I have to have this dy dx, right? And this is really a chain rule here. Derivative of the outside evaluated at the inside times the derivative of the inside. You can think of this as being a chain rule too, but the derivative of the inside is 1, right? So I have, what's the derivative of x squared? That's 2x. But the derivative of y squared with respect to x is 2y times dy dx, right? So does anyone have any questions where that came from?
I don't have a question where that came from, but for the graphs, are you going to give us like a graph and say what is going to be the derivative of this graph?
There's really no graphing in this section. That will be exam 3.
Okay.
Exam 3 will be very intensely on graphing the derivative on top of functions and when's the derivative positive, when's the slope positive, things like that, being able to evaluate that in certain regions. So we'll get to that in chapter 4. Question?
Are there going to be any questions that are like
Log of a function?
Yeah.
Like log base b or log base 5 versus ln of x? I don't foresee them. They really don't come up. Question?
I get confused on the difference between b to the x and b to the u. Could you give an example of equation in each form?
Okay, generally we deal with e, right? B is e. So e to the x is a function. This is just e to the x. But if I have e to the sine of x, I'm going to call this u, right? So my derivative of this is going to be e to this times the derivative of this. It's just another way your book simplifies the chain rule within e to the x, right?
Isn't x a function?
X is a function, but u is a function of x, right?
That's where I get confused.
They're just saying, okay, let sine of x equal u. So if I wanted to find the derivative of e to the u, I take e to the u times the derivative of the inside with respect to x. But u is a function of x. Does that make sense? Let me think if I can think of another way. They also use this in the trig. Let me finish this problem and then I can come back to that. So here I get dy over dx equals minus 5y cubed over 15x y squared minus 16y. Then I plug in x equals 1, y equals, at the point 1, comma 2. And I get a number. This number is my slope, right? So then I have y minus 2 equals that number times x minus 1. This is the equation. Because I have 3 times 5. Make sense? So this is an example of implicit differentiation, which is 3.1, which will be on the exam. So you'll be asked to do implicit differentiation. You did implicit differentiation on the take-home quiz, which you guys did very well on. So yeah, exactly. So it should be no problem. If you recall this example here, this would be just straightforward. Derivative of the outside evaluated the inside times the derivative of the inside. Did you guys do? You did implicit differentiation on the quiz in class, right? This was the example of implicit differentiation, right? Pretty straightforward. So if you missed that, go back and make sure you both, number 3 and number 4, something like that is very likely to show up on the exam tomorrow. I have exam 4. So
Yeah, it's quiz number 5.
quiz number 5, yeah. So this is, you've seen this problem before. Basic problems. Find the second derivative. If I give you a polynomial, differentiate it once, then differentiate it again.
So in that question, do you have to differentiate y?
What? Here? Y is written explicitly. So if I find dy dx, I can differentiate the right-hand side, and then finding the derivative of dy dx is the second derivative. So I differentiate the derivative I've already found. Right? So my first derivative is 8x to the 7 plus 12x squared. The second derivative is.
So how can we make sure that we don't need to find the derivative of y itself? So
If y is by itself, then when I differentiate y, I get dy dx. But in this example down here, y is not by itself, right? So if I differentiate this term, I get 3x squared. But if I differentiate this term, I get 3y squared dy dx. And then differentiating this term, I have to use the product rule.
yeah, but the one above we can use even the ln, so we would have 1 over y and dy over x too.
Here,
Yes. How about if we use the ln?
you wouldn't use ln here. No, you could. It would be quite a bit more work though. Ln of y could equal 8 ln of x plus 12 ln of x. But that's going to be the derivative here. I have 1 over y times dy over dx equals 8 over x plus 12 over x. All this is multiplied by y, which y would be x to the 8 plus 4x cubed. Now, if I need to find a common denominator and simplify, you're going to end up with the same answer for dy dx, and I can show you. So dy over dx, this would be 8 over x plus 12 over x would be 20 over x, right? It would be 20 over x times x to the 8 plus 4x cubed. So what do I end up with?
This is just way, it's so much easier.
Yeah. Yeah, why would you do it? But would it be the same thing here?
So the only time we really need to do this is if y isn't alone.
Yes. In this case, no. ln of y is called logarithmic differentiation, not implicit differentiation, right? So, in the example, implicit differentiation comes up on the final exam. Logarithmic differentiation is a possibility, but it's not a high likelihood. And honestly, it comes up more in the cases when we're dealing with L'Hopital's rule, right? When I have 1 to the infinity or infinity to the infinity. Sorry, 1 to the infinity, 0 to the 0, or 1. There's 3 of them. Which one am I missing? 0 to the infinity. Those 3 indeterminate types. Then I have to use logarithmic differentiation. So in the past, I've given. So I have bonus built in some of the exams, and this would be an example where I say use logarithmic differentiation. This would be where you would go about taking ln of both sides, simplifying, and then differentiating and solve for dy over dx. You guys did an example like this on Wiley, right? It's the same application there. It's a lot easier to use logarithmic differentiation when your function is really, really complicated, because the power of logs allows you to simplify it to something relatively easy to differentiate. Right? So that's logarithmic differentiation, and that comes up in 3.2. Yeah, so there's an example, number 5 in your book. And that's very similar to that, right? So you're just, and you guys did this on exam 1, but you didn't differentiate it. So you got it down to this point. And then differentiating it, it's just term by term. The derivative of ln of y is 1 over y dy dx. The derivative of 2 ln of x is 2 over x. The derivative of this, I hold the constant, 1 over the derivative of the inside, 1 over the inside times the derivative of the inside. So you see term by term, relatively simple. And then simplifying, you get your derivative here. Right? And that's very, very similar to example number 5 in the book over 3.2. And then the last thing covered on the exam is 3.3, and I know we spent quite a bit of time on the derivative of the inverse, some examples of that. I'm not going to test you over anything more complicated than what you did on Wiley. Right? So pretty straightforward. The same thing with the derivative of the inverse trig functions. So 3.3. So the last part here, I know some of you are still writing this down, but if I get 3.3, know that the derivative with respect to x of sine inverse, again, I'm going to write this u, so I can maybe explain here. U is a function of x. So the form, the outside function is sine inverse. The inside function is u. So my form here would be 1 over what? Right? Times the derivative of the inside, that's what du dx represents. So if I have, what is the derivative with respect to x of maybe sine inverse of 5x squared? Oh, sorry. So I'm going to take this, I think. At a certain point, you guys can finish that if you're not done there. Here, 1 over the square root of 1 minus 25x to the 4th, right? Because that's 5x squared squared would be 25x to the 4th, times the derivative, this is u, and what is the derivative of u? 10x. So I could write this as 10x over the square root. Question?
Which of these would we need to know?
Sine inverse and tangent inverse. Cosine is just sine inverse negative, yeah, right. So honestly, after this section, they really don't come up again until Chapter 7, which is in Calc 2. So if you don't take Calc 2, you probably won't see this again. If you do take Calc 2, you will see this again. So if you know it and you're comfortable with it, it will just make that section in Chapter 7 a little bit easier to understand, being able to see this.
So we don't need to have secant?
No, that's fine. The secant's like sine is just the absolute value of u there. So no, so I will test you over these two concepts, so to know them. Be familiar with the other ones, but you don't have to have it memorized. and know at least some form. You can derive them by yourself, right? And we did that in class. If I say I'm going to let x equal sine of y, if I was to graph sine of y, then this is going to be x1, and this is the square root of 1 squared minus x squared, right? If this is sine of y, or this is angle y, sorry. So y equals sine inverse of x. So this is angle y. And if I take sine of y, I get x, so I get this relationship. So if I was to differentiate, if I want to find the derivative of the inverse, we know that the derivative of the inverse function is 1 over the derivative of the function, but evaluated at, let's say, the derivative of this function, so this would be cosine of y, right? From that form, I take the derivative of this side, but evaluate it at y. So what is 1 over cosine of y? Well, cosine would be over 1, right? So I get 1 over the square root of 1 minus x squared. So that is the derivative of the inverse of sine. And you can do the same thing with cosine and tangent and secant and cosine and so forth from that. So if I let x equals cosine of y, then I have y equals cosine inverse of x. So if this is my angle y, and cosine of y is x, then this is x over 1, and this is the square root of 1 squared minus x squared. And then the derivative of the inverse function is going to be minus sine of y. So if I look at the picture, it's minus 1 over the square root of 1 minus x squared. Right? All right, I will see you guys tomorrow for the exam.